Hi everyone. Good morning. I'm using a new device here, so hopefully everything is working. Let me know if you are not hearing me. Yeah, if there is any issue, let me know. Otherwise, we can continue. So this is May 21st session. I'm Ali Rasek, and this is this Tuesday's session of Civil 459 Earthquake Engineering. Basically, we are here this week of 21 May, 24 May. We are still continuing with module number 1, but that's fine. However, we have a strong deadline and this week by about Friday. I want to receive all the draft work plans. And if you guys have questions or concerns, just send them to me or to Benam and we are able to help you. What I'm saying, about 26 students are in. We give everybody 1 more minute and then we can continue. Okay, 11:05 already. On Friday, let me add one more person here. Okay. Yeah, last Friday we were working our way through some examples here, and I go to almost where we left off. We went through quite a few good examples on estimating stiffnesses and masses of the system and coming up with the period of vibration of the system, such as a bridge here. We did very good examples here to review our general knowledge of dynamic characteristics of the system. And here, so with this one we went through, we looked at this shaking table, a small shaking table at the University of California at Berkeley. Your shaking table at UWIC is almost the same size, and we will have a session on June 7 where we will watch some shaking on that table and we compare it with our knowledge of basically dynamics of structures that we are gaining right now. And we checked decaying. Let me put this microphone here. Sorry, slightly different setup here because I'm at the office. Okay, so we discussed the decaying free vibration, and we could estimate very quickly. That was a nice and quick way of checking the period of the system and damping of the system. And we went through the steps, and period was just seeing how many vibrations did we have and in how long a time, and the ratio was the period of the system estimated at 0.273 seconds. And for damping, we had this solution that I previously introduced to you based on the logarithm of the change in amplitude. And in this case, we have acceleration amplitude. Similarly, we could do with deflection amplitude. And the change in acceleration amplitude gave us, that ratio, we could use it to assess the damping of the system. Now we want to use a slightly more advanced solution, which a lot of times results in more accurate estimate of the period of the system. And this is called, we previously introduced this method. It's called the half power bandwidth, and we use that method. Again, so this is a shaking table, so this is like an experiment in a way on this particular type of a structure and material. Material is plexiglass and frame is built out of it. And for half power bandwidth, what we do is we keep on the excitation, meaning that we apply a harmonic excitation with constant frequency and amplitude. And then we measure the ratio of excited acceleration to original acceleration. Base acceleration, that's the acceleration at the base, which is on the denominator, such as, I mean, it's as if it's ground acceleration. It's the way to kind of think about it. And this is the top of the structure acceleration on the top of your structure here. So obviously we have some resonance when your frequency of excitation gets close to the frequency of the system. And so in the horizontal axis, we are just monitoring different frequencies of excitation. So the structure was excited by these different frequencies, which changed between about 3.3 hertz and went as high as about 3.9 hertz. And while making those changes, maybe like whoever performed this test, they originally did this decaying free vibration, so they almost know what to expect to be the period of a structure and the frequency of the structure, which is the reverse of this. And therefore, they started from a value smaller than the frequency of the system or structure, and they ended with a value higher than that, so that they meet the resonance. The resonance has happened at 3.59, where we have the highest response. So now we have like a bunch of points on a curve based on different base excitations. And for each case, we have also noted the level of excitation, meaning the ratio of the acceleration at the roof level to acceleration at the base level. And we noted these values, we created this curve, and we can go through the steps for determining the damping of the system. This is the half power bandwidth solution. And if you remember from previous sessions, the solution was to determine the resonance amplitude and divide it by a square root of 2, and then draw an horizontal line. Now you have like a lower point and upper point. Upper point is FB and lower point is FA, and FN is the resonance frequency. So each one of these are our frequencies. If I said amplitude, I mean frequencies. So we have FA, FN, and FB. So in this plot, the frequency is normalized with respect to natural frequency. Therefore, the middle point is 1, where frequency is the natural frequency. But you could also do this, not normalize it, and that leads to the same outcome in a way. So going through the exercise, the highest amplitude was 12.8 for acceleration, or the acceleration ratio, and divided by a square root of 2, we got 9.05, the other straight line, and we have FA 3.44 hertz, FB 3.74 hertz, and the maximum, which might not be exactly the average, is 3.59. And therefore, we can estimate the damping, the difference between the upper value, FB, lower value, FA, divided by twice the natural frequency. It gave us an estimate of 4.2 for damping ratio, 4.2%. So the previous estimate, how much was that with a simpler solution? We got 3.96, almost 4. And now with a more accurate solution, we are getting 4.2. So they kind of in agreement with each other. However, the second solution is considered a better solution. And as I think previously I told you guys, this solution is, again, both applicable to numerical studies and also to experimental studies, such as what I showed here. That's about the half power bandwidth. Again, we continue with trying to assess earthquake response for different structures based on what we have learned so far. Here we have a lollipop structure with a mass on top of a cantilevered column in a way. And the mass is 1650 kilograms. The height is 4 meters, and the cantilevered column has its nominally 100 millimeter pipe, and the diameters, outside diameters 114, and inside diameter 102 millimeters in millimeter. Second of inertia. A second, I should admit one more person. Yeah. So second moment of inertia, moment of area in a way of the cross section, was important in assessing the stiffness of a cantilevered column or beam, and like it was calculated in the book that I used, probably Chopra, and maybe you can do the hand calculation yourself for these specifications, which was 301 centimeters to the power of 4. So second moment of inertia area has a power of 4, like length to the power of 4 unit. And the elastic modulus of a steel, typical, it's always about very close to 200 gigapascals. We want to find the response to horizontal El Centro earthquake, meaning that the base is excited in El Centro earthquake. And what we want is the peak deformation, like we want to know how much this mass moved during an earthquake, the maximum value of the movement. And we want to get the maximum stress caused by bending. So when this mass moves right and left, it creates bending in the column, the pipe, and that moment, that maximum moment at the base will result in a bending stress. Going to the next page. Yeah, again, this is like a kind of equation you can find on internet or ChatGPT, but you should generally be aware of it and be able to verify the correctness. So when you have a cantilevered beam, the coefficient is 3, but if you have a column which is prevented from rotation both at the bottom and top, it becomes stiffer. And the coefficient, I believe, is about 12. But that's, yeah, like you should generally have the knowledge, know the resources, but sometimes when we are forgetful, you are welcome to use the searches. And so the stiffness of such column is directly related to elastic modulus and the thickness in a way of the shape. However, when your length increases, the stiffness reduces. That's also some kind of engineering judgment. You can even feel that when you have a longer column, it should be softer for lateral deflections. Going through the calculations and the stiffness in terms of force divided by deflection is about 28,000 or 28 kilonewton per meter. Calculating frequency, again, you should have a sense now that frequency increases with the stiffness and period reduces with the stiffness. So you should be able to double check the numerator and denominator. Mass, we had it, and it's like 28,000 kilograms. Why does it look reverse? But yeah, I don't know why I had a typo here. So so I should fix this for next year. I think this is the reverse of this, but the end result is correct. Obviously, 28,000 divided by 1600 and a square root. So the period was 4 in terms of, frequency was 4, or the rotational frequency in terms of radian per second. And from which you can obtain T. That's interesting. You can fix this and upload it one more time. But yeah, generally, I expect you guys to have that sense because these typos happen in the work, and you should have a feeling that a stiffness contributes to frequency, so it should be on the denominator. But the end product is correct, and the result is correct. The period of your system is 1.52 seconds, which is important. And now to assess the response, we are going to use the spectral response that I think probably we discussed the exact same earthquake in the previous sessions or similar earthquake. And at that time, I introduced you to this notion that was in the previous generations, even one generation before me, it was very popular to show the perpendicular like axis for velocity and acceleration and deflection. But for us as well, for me and for you, this is good. It gives you good understanding. So it's good to go through this one time at least, although we are all users of computer systems, and nowadays with printing devices, you just, even if you want to print, you print them separately, but it gives you good understanding how they are correlated to each other. The deflection spectra, pseudo acceleration and pseudo velocity could be related to each other if they are plotted appropriately on a logarithmic scale. Now, we said that the period is 1.52 seconds, and we want to, like, one of the intentions was, one second, we can see it. Okay, sorry about that. One of the intentions was to assess the deformation, and so we can read the deformation basically from the deformation axis, and we read it to be 12.5 centimeters. So this one, the unit was centimeter already. And acceleration is important as well because it helps us with assessing the forces. And using this, like it's obviously greater than 0.2. And if you look more closely, probably you can read a value close to 0.22 g, and the unit is g. Velocity, we normally are less concerned with velocity. Deflection is important. You will see it once and again during when we do NBCC as well, that we want acceleration to be able to get the force, and we want the deformation because we design for deformations as well in general. Like one example is that if there are two structures side by side, we don't want them to hit each other. And we also don't want the structures to deflect too much, as it might cause lack of stability. Now, as I said, we have the peak acceleration in terms of g. So we multiply it by g, and we multiply by mass, and we get the total force, like the maximum force, lateral inertia force that this structure will be experiencing during El Centro earthquake is 3.5 kilonewtons. Now again, back to the structure, repeating the same calculation, 3.5 kilonewton was the estimate of the load applied to the mass, because in earthquake, the mass actually sees the load, because earthquake is acceleration and it causes inertial forces in the mass. So the maximum force applied to this mass at the roof level or at the mass or tanker level is 3.54 kilonewtons. And with your structural analysis calculation, you can obtain the maximum moment at the base, force multiplied by the arm, 14.2 kilonewton meters, and you can obtain the bending stress. This is again from the structural analysis books, the courses you previously had, that for a circular section or for any section, basically, if you have the eye and you have the maximum distance to the edge, in this case radius, you can calculate the stress, the maximum stress. So the maximum stress that this steel pipe will experience during earthquake would be about 270 megapascals, which could be used in the design checks, comparing with the steel capacity. And all different types of steel, they have the same elastic modulus, but they have different yielding stresses. This could be, I think, probably okay for, or close to okay for some of the building steels. Or, I mean, you should also look at your specs. So, but doesn't look like a too huge number. Say, a steel from your steel book is probably about 350. But this could be even higher strength. So it looks like a pass. Yeah. Any questions on this slideshow? Oh, I see there was one comment. Oh, sorry, I missed this from the start of the class. Do we email it to you? I prefer that there be a bright space submission. So if I didn't succeed in creating it, can you confirm that it's not in there? Then I will ask Benam or Armando to add it. I want to have a submission there so that everything is clear. Okay. Okay. Thank you. Thanks for informing me. Yeah, if it's not there by Friday, definitely email it to me. But I will ask Benham and Armando to look into this. Make sure that there is a submission column in there that you can submit. Thank you, Jackpot, for bringing this up. Other questions and concerns? Okay, good timing, 11:28. I can give you 1 minute almost and then jump into the next slide. I have also uploaded the model. Hopefully it opens on my computer as well. Yeah. Opened. So we have a SAP 2000 model. Generally, I'm hoping that you guys have some experience with SAP 2000, but it's one of the best softwares for self-learning. Even sometimes I don't use a feature for a long time and I want to relearn it. Excellent videos and YouTube links and knowledge base links that explains everything. So I'm not seeing any issues with learning the software and using it. However, we go through a dynamic case in this session. SAP 2000, single degree of freedom. Yeah, the SAP 2000 model is what I just showed to you. It's basically a one-story frame with the height of 3 meters and length of 6 meters. It's like a portal frame, as we called it. And I have listed a few important tasks when you create a model. Be aware of your material and section. Material means that you have used a steel, and section means that what section steel profile from your steel book or from the vendor, etc. You should know what the profile is. In the last case we just discussed, it was a tube, like hollow tube. So you should define your section as well, because most of our work is based on frame assumption, meaning that the finite element solution doesn't care about the section and it should be defined like the frame should be defined by its section. It doesn't discretize the section, which is an excellent solution and very efficient for our type of work. Build geometry, meaning that high level, what is the geometry? We have 6 meter by 3 meter geometry. Assign masses. So whenever we have the dynamic solution, means that we have mass in the system. So dynamic is correlated with mass. You shouldn't forget about the mass. You either define it as the mass of the frame members or the mass concentrated at the nodes, or both of them. Restraints, meaning that the whole system should be restrained. So you have supports, like here we have two supports here and here at A axis and B axis. And the picture indicates that the support is like in both translational directions and rotational. And the other direction definitely is restrained because it's a 2D problem. So you have a 2D problem in X and Z. Definitely you are restraining the Y direction. However, about the two other directions, you should also put enough restraints and I mean, based on their physical issue, that physical phenomena that you are modeling, which is your building, and you know that it has foundation and it's anchored into the foundation. Therefore, there is proper rotational support and proper displacement support in there. And you assign those properties as restraints. Define time history records. So with the computer model, you can do what we call time history analysis, or preferably we sometimes call it response history analysis. I think SAP 2000 calls it time history analysis. And in a way, traditionally, it's always has been famous as a time history solution, but preferably we should call it response history solution. So you have the acceleration record defined within your model, and there are other loads applied to the system, like dead load, weights. Although you might have mass, but you should be, like mass is not exactly the same as weight. You might have mass and also apply the gravity so that you have a dead load. Lateral load, sometimes we have equivalent lateral load, as I mentioned. You will do that a lot using the NBCC. Instead of applying the base excitation at the base, you apply the equivalent lateral. Modal analysis, it's separate, it's not part of the other load patterns, but it's a loading or a solution by itself. It produces the period of the structure and the mode shapes. We had other load cases as well. We will discuss it, ramping load or harmonic base excitation or the real earthquake excitation, which comes from this time history. Then when we are confident everything is in place, we run the analysis and we review the outcome. Outcome or output is mode shapes and periods from modal analysis and the responses to other load cases. Yeah, so you, as I said, you always should be, sometimes we trivialize it, but it's very important that the material and sections be basically checked and double checked, like two independent people look at them, because if they are not correct, then it's like, I mean, you cannot trust the outcome. The material was, if I can read it correctly, steel with a yield of 50 KSI. 50 KSI is almost the same as 350 megapascal. So that's the material that is used. However, we are not going nonlinear, so specifying the yield is not super important. But we have the awareness that most of the steel that we use is 50 KSI in a way, or grade 50 KSI, which means that the yield is 50 KSI. And if you change the units from imperial to SI, which is more, at least academically, more practiced in Canada, then you get about 350. For industry, generally it's good to know both of them, try and be able to switch between the two, because in Canada, there is still some imperial units, like grade of this steel is called 50, which means 50 KSI. And because we all live very close to the US border, so there is high possibility that we work on US projects as well. But I mean, it's trivial. Therefore, I recommend reporting in the standard SI definitely, but be able to understand the other unit system as well. Imperial. Unit weight in terms of kilograms per cubic meter is about 7,700, which is correct. And yeah, I'm looking at the biggest screen, but looks like the resolution is not perfect. So maybe next time I just keep it on my laptop screen. Modulus of elasticity, again, as we said, 200 gigapascals, so about 2E11 for any type of steel. Poisson's ratio is given there, which is probably not used for our work, but it's in there. Thermal expansion, we are not using it. Yield stress, as I said, after changing to SI unit is about 350 megapascal or 3.5 E8. And other ultimate trend for this material is also given, about 4.5 E8 and other parameters, but none of them will practically be used in this example. But you guys should always be aware of the specs that is used in your work and the assumption. Then we have this section, I section or W section, which is built up out of this material, steel, and all the dimensions are here. It says the material is really grade 50, which was defined on this side. And you can have modifiers applied to it, but it would be more hidden. I don't suggest using hidden stuff that couldn't be double checked because it causes issues. And yeah, normally there's a table in most of the software where you can import the standard profiles. So probably that's what has happened in this case as well. And going to the submodel, if I can still find my way here, it's normally under define. You can define the material and sections. So we go to material, jumped into my other screen. Yeah. And this is the grade 50 steel that we were looking at. So jumping to the other screen. But yeah, so everything that I was showing to you, it's implemented in the model, and you have access to the model. You can scrutinize it. Going back to the slideshow. So very, very important, always throughout your career, check the material properties, use the correct value for your project. Be very careful with your assumptions. Mass, so appears that in this case, the nodal mass is applied, 20 tons total. So 10 tons on each node. That was the floor mass, which was probably concentrated there, and floor mass is a lot greater than the member mass. So the program is showing it directional mass because the program is capable of, for certain purposes, you can only have horizontal mass or only vertical mass, but generally for most cases, the mass should be identical in all directions as the physics of the phenomena. All masses are the same in all directions. Sometimes for computational purposes, you only want to apply it in a certain direction. Okay, going back to the model. Sometimes you can right click. Okay. Bring it back. See everything assigned to every node. And as you see, the mass is in 3 directions and 10 tons in each direction. The unit is shown here, Newton and meter, and probably centigrade. For thermal, Newton and meter correlates with kilograms, so the mass is in kilograms. Okay, and here, what do we have? Constraint, we don't have any constraint. We have restraints there. Anything related to movement out of plane was restrained. So, and all the rotations are restrained, if I'm saying correctly. So rotation in all 3 directions are restrained, as if we have a very rigid floor here, which doesn't really allow rotation at x2. Deflection is only restrained out of plane because there's no out of plane movement. I mean, or we are not interested or concerned about out of plane because this study is focused on in plane movement, X direction mostly, not even Z or Z. Anyways, so just wanted to, as I promised, I want to just slightly walk you through this SAP 2000 example, although there are very good resources on the internet. And it has been for many years, SAP has been the SAP 2000 has been the most important tool for structural engineers. So highly recommend that you have some proficiency with this software. The software could calculate, as I said, run the modal analysis and calculate the primary period of the structure, which is 0.28 seconds. Let's look at this. Say if you want to see deflected shape for modal, it shows the mode shape of the first mode of a structure, and the period is about 0.28 shown here. And yeah, the beam has remained pretty flat, no surprise because we forced that. As you saw, we didn't allow any rotation at this point or this point, which again should replicate the physical reality of the system. This was intended for a slab system or the roof system, which is very rigid and doesn't really allow any deformation or rotation in the beam. But you could do, like if you had not used, or you can play with this, modify the restraint here so that rotation is allowed here, then you will obtain different frequency and different period, which is a good thing to play with. Yeah, so this model was used for a free vibration test. Basically, a load case was defined as shown here. For free vibration, what did we want to do? We wanted to apply a load and then suddenly release it so that the structure starts moving and gradually damp out. So the time history is defined where the loading function increases from 0 to 1, gradually applied to the system. and then is suddenly removed. After 1 second at 101, at 1.01, there's no load. So that the force is applied and then we allow it to keep on moving. This load case is called time history because the time history solution is used. Lateral load, and the nickname for this load. And here we indicate that the load pattern, what is the load pattern, which is the one that is shown on the right side. So load is applied by a lateral load pattern, and the function name is mentioned here. It's not scaled up, so it goes to a maximum of 1. Time stepping data is here because you are running a time history analysis. It's sensitive, we discussed it, we even showed the theory background, why time stepping is important. Number one, some of the solutions become unstable if your time steps are too large. And number two, even more important, you need a smaller and smaller time step to increase the accuracy. A linear time history is performed, and it's a modal time history, so that the program is able to do direct integration or modal. Both are beneficial. Sometimes modal results in quicker solution. Especially in linear, both should be, after when they are converged, they should result in an identical outcome. Frequency domain, I barely use it. It's mostly frequency domain solutions. That's what geotechnical engineers are interested in. We are mostly interested in direct integration and sometimes modal, because modal is faster to converge, but most of the time direct integration. Especially nowadays, we are less and less concerned with the expense of the analysis because it's becoming faster and faster. So direct integration is what we normally look for. Let me see if I can put it out in the real model. Didn't we say load case? In different load cases, we discussed probably this one, lateral load. And modify show. Almost what we were seeing there. And this is a static. No, we want we want one of the time states. So forget about this one. So that's lateral under static. Lateral under dynamic is this one. Yeah, exactly same as those screenshots. And we already discussed a lot of these things. Mass source is mentioned here. Just pretty much every mass in the system should be used. Output time step is different than the time stepping for analysis. So the analysis duration, we have said that during the analysis duration, use 400 steps. That's the way these programs have 2000 works, that we should tell it how many, the number of total steps. But sometimes in some other programs, we say we want this duration, and the time step should be, say, 0.01 or 0.001. Here, maybe something that I missed is the damping. So we have defined a constant material damping of 5% on the system. So we are dictating 5% damping. Back to the slideshow. Now, what are the outcomes? We can see those outcomes or outputs from the model. This first plot is the displacement. This is when we were loading it, and then we remove loading and we allowed it to vibrate and gradually damp out. So obviously the deflection is reducing and the energy in the system is dissipating. We have dictated 5% damping. Similarly, acceleration, which is also important to us. And we have noted the maximum values for both cases. So in this case, 8 millimeter. In this case, 4 meters per square second or 0.4 G. We can even ask the program to output the base shear, like the shear at the base of the structure. And the maximum value is 80 kilonewtons. And yeah, as we expect, everything is behaving as we expected. Yeah, so if you want to use this solution for just back calculating the damping in the system, we go from one maximum to the next and use this solution to calculate delta and use delta over 2 pi to back calculate damping. And also we can use this solution to get the natural period between one maximum and the next. Looks like we could visually see about 0.28 seconds. That's what the model analysis was also giving to us. So double checked. And going through these steps should also give us a number very close to 5%, because I mean, it's in this case, it's trivial because we dictated 5% damping, so it should be no surprise. But it's a good exercise just to see you specified 5% damping and you can calculate 5% damping. Okay, other questions? Not in the chat room. Yeah, as I said, always feel free to open your mic and ask questions. So a harmonic excitation exercise was also performed. Again, a time history function was defined, which is basically a sinusoidal load with a scale factor of 4. And most of the other specifications remain the same. Damping also remained as fat damping ratio remained as 5%. Time stepping also the same, but this is a longer analysis, therefore more time steps in there. And the function that is mentioned here is defined as a sinusoidal function with a maximum of 1. And I cannot see the period or the frequency of the forcing function. So it starts from 0, goes to 1 in 0.25. Oh, sorry. Yeah, I cannot guess, but we can see what is the frequency. I think here we try to emphasize that the period is 1 second, and here it says 1 second. Going from 0 to maximum takes a quarter of the cycle. So a quarter of a cycle happened in 0.25 seconds. So the period is 1 second. That's what I'm seeing here. And the function goes to the maximum of 1, but a scale factor of 4 is used so that the maximum acceleration is 4 meters per square second, which is almost 0.4 g. So everything matches. Again, we use that excitation, apply that excitation on the system with a maximum value of 0.4 g, and the program is able to basically output the pseudo spectral acceleration as if this is an earthquake, but very unusual earthquake, which is like harmonic. So harmonic excitation can also have a pseudo spectral acceleration, but it has a very regular form. And as we expected, this is a good exercise in getting the pseudo acceleration, because unlike earthquake, which you have a lot of zigzags and ups and downs, you only have one up exactly at the period of the system, which was 1. That's where the maximum excitation happens, the resonance happens. The program can produce that for different damping ratios. The lower the damping ratio, the higher the resonance. Everything as expected. And versus, if I'm not wrong, this is the one on the right is the spectral curve for probably for, okay, no, this is, I forgot almost from last year. So the program allows you to zoom in certain location. So I zoomed in and I took the screenshot here. And so this is basically just like focusing on this area. And because we are interested in the response at the period of the structure. So this is basically using the response spectrum solution, inputting the period of the structure, which we know is at about 0.28, and reading the response, which is about 0.5 g. So the response should be, the maximum acceleration the system will see should be 0.5 g based on the response spectrum solution. Now looking at the output of the system with that base excitation, in a way, surprised, the STD acceleration is at about 0.5 g. So the maximum acceleration gets very close to 0.5 g in the horizontal direction. And base shear is about 100 kilonewtons, which is almost corresponds to or almost identical to multiplying the maximum acceleration by the mass. Mass was 20 tons, if I remember, 20,000 kilograms multiplied by the maximum acceleration gives you the 100 kilonewtons. So 20,000 multiplied by 0.5 is 10,000. G is close to 10. So that's 100,000 newtons or 100 kilonewtons. Also, you can observe the maximum displacement, which is 10 millimeter. You can get it from the time history output. So basically, in a way, you verified the response spectrum solution. Use the response spectrum solution to get an estimate, but also read the results from the program. Now, the most important solution that we will be using a lot, or maybe you will be using it in your project as well, is using the real earthquake. So the real earthquake is also added there. If you see an error message there, this is an earthquake from the default sub 2000 records. Then you can point it to the folder in your sub 2000 where all the records are kept, and you can find that record, which is EQALT1, just to, if you want to just exactly repeat what we have here. And so you can define that function, which is the earthquake function. And then, yeah, so they're like a typical, like reading in the data, the first two lines, this is a text file that it will be reading. And the first two lines are specifications, and you ask the program to skip those. And starting from the third line, it reads the acceleration data and inputs it. Right-hand side, using that function that is defined here to define your earthquake. And a scale factor of 0.01. I think the function, you should read the specs on top of that text file. The function was probably in centimeters per second, while the unit of your analysis is meters, therefore multiplied by 0.01. Yeah, same descriptions, linear, modal time history or direct integration time history, transient analysis, damping of 5%. You want to run it for 30 seconds and 100 steps in every second. That's 3,000 total steps. Same idea, but on a real earthquake. Yeah, so I have included the typical data file. I expect you guys to just open it and look at it as well. Some digits showing the specifications of the earthquake. However, you know that the output, the earthquake record is in 8 columns. You can see that. And the time steps should be mentioned on top, which is 0.01 second. The unit, which is centimeters per square second, centimeter per second. So you should be aware of that. Then you use a multiplier of 0.01 because the unit of your analysis is meters. And the maximum value is 0.4 G in this case as well. All right. And the location is this folder on your computer. So if you are seeing like error message that the program, after downloading my version into your computer, if the program cannot find the function, you can point it to this folder. Again, you can have the program create a spectral or pseudo spectral acceleration. As we previously said, pseudo spectral is even more popular than spectral, or Chopra argues that pseudo spectral is a better tool as well. So we should be, although we forget in practice, we should be more using pseudo spectral. But sometimes we alternatively use a spectral acceleration or pseudo spectral acceleration. This is shown for 1% damping and 5% damping. Obviously, 5% damping is lower. It's damped more. And again, zooming into this area that I have shown, for 5% damping, and a period of 0.28 second, we expect a response of about 1.3 G. And the more correct time history analysis appears that it has given us 1.1 G. So pseudo, I mean, as response spectrum solution is normally we consider it to be more conservative. So it gives you higher value, while the response history analysis or time history analysis is more correct in a way. So this is the more correct solution when you read the response from the program. The maximum acceleration in the system was 1.1 G. Deflection is also important. And here I emphasize absolute acceleration. So absolute acceleration should be used in design rather than relative acceleration. Displacement, normally we are interested in relative displacement or deflection. How much the top of a structure deflected with respect to the ground. That's the important factor for design. And that has been 25 millimeter in this case. The program output base shear of 260 kilonewton, which corresponded with 1.3 G. And the acceleration, if it's acceleration, top of the roof of the structure, base of the structure, there is amplification. So roof is seeing a lot higher acceleration. Yeah, that's the same 1.1 that we discussed. So the roof level acceleration is, as we expect, higher than base excitation. Yeah, that's it. So that's a very good exercise to refresh your knowledge of SAP 2000 and also fully, like just by playing by your computer or with the software, understand the concepts that we were discussing so far. Now, questions about SAP 2000, 1D analysis, 1 degree of freedom, 1 degree of freedom. We should call it, it's a 2D, but 1 degree of freedom. That's what we showed here. So this is a 2D structure, but practically we allowed it to move only, like the top of the structure moves horizontally, and there is only one deflection to measure, which is horizontal deflection. So that was a 1 degree of freedom, while the structure is really 2D. Again, questions? I'm not seeing anything on the comment section. Well, I'm hoping that you guys are doing well with forming your teams, etc. Let me go back to this one. I have not really looked at it. Looks like it was working as far as creating the teams, but you said that you couldn't upload the, yeah, okay, I'm seeing some numbers here. Oh, beautiful. Looks like we have 8 teams. Excellent. That was a important step. So you can keep on using the same group number. However, I will reach out to, okay, hopefully 10 more minutes on battery. Well, let me see if I can reduce the demand. transferring the screen sharing anymore. You are seeing me. Anyways, the question was more important. I don't know how I missed that one. Zoom meeting. Okay. Already, let me go to the chat. Yeah. How to assess the educational version access? Or isn't it working? I should call your IT if it's not working, because normally you should have access to that. Yeah, let me write it down. So I think it's related to like you have a license, which is, it's not even exactly educational. It's related to UWeek registration. You should be able to download it and use that license. So contact your IT and I will remind them that for this course, you guys should have access to the license. Maybe it's not the latest revision of SAP 2000, it's like one of the last versions. Did I answer your question? So I think you should do it through UWeek system in a way. Access the license through UWeek. Maybe you should VPN or those kind of solutions. But your IT, I will email them, and when they tell me, I will just broadcast it one more time. Other questions? Hopefully I answered the recent questions. So we have an issue with SAP and an issue with uploading the work plan. And we had one typo. I should fix that. Yeah, feel free to ask your other questions. This is trying to have a preview of what we do next time. No, 2.1. So it's module 2, which is like multi-degree of freedom. That's what we want to do next time. And or starting from at this moment, maybe we can look at it for a few minutes if you guys are not asking questions, so that you know where we are heading to. We want to move on to the multiple degrees of freedom systems, and basically something like a two-story building where you have separate masses on each story, and this could be simplified, but as low as 2 degrees of freedom system, because the first floor and second floor are really acting independently. It's difficult to, or impossible to correlate it for general earthquake. And we have talked about the equation of motion for single degree of freedom. For multiple